So I want us to think of any sort of closed loop. Doesn't have to be a circle. I drew a circle. This shape has area equal to capital A. And let's draw a magnetic field inside of that loop. Let's draw a second loop. That's smaller, but in the same magnetic field. I'm going to try and replicate the field I drew over there as best I can. Which loop is enclosing more of the magnetic field, left or right? Left. That's the whole idea behind Flux, is that the loop they're in the same strength field, B is the same for both, but the loop on the left encloses more of the field than the one on the right. So this, of the two, has the greater magnetic flux. And this has the less magnetic flux for the same field. This concept is going to seem kind of arbitrary right now. I promise it is a useful one that we will discuss why it matters in a moment. But right now the idea is just more of the field enclosed in the loop is higher flux. So we're going to make a definition now. This definition is going to generate this, or go after this idea. Stronger field will be more flux. Bigger loop will be more flux, more area. So the product of those two serves as a definition for flux. If you have a stronger field, if you have a bigger area, overall, more field strength is enclosed by that loop. The symbol we use for this is a capital phi, which looks a little bit like a TIE fighter. So this is magnetic flux, and it's the Greek letter. It's a capital phi. So you're familiar with lowercase phi, that looks like that. From math class, this is the capitalized version of that. There is one more addition to add to this definition, which we'll use a prop to explain. I've got my loop here. If the loop is oriented this way, lots of magnetic field can flow through that loop. This wire, the Sharpie here is the magnetic field. It can flow through. It can flow through. There's some flux. What happens if my loop is oriented this way? How much field can through the loop? None of it. This way. What if it's like tilted at 90 degrees? Some, but less. So I get. Okay. Leave the full screen. We need to add in some idea with this, which is we're going to throw a little perpendicular on the area there, which is the amount of area perpendicular to the field. Let's talk about the convention for the angle that's used when defining the amount of area perpendicular to the field. I'm going to draw a magnetic field that's going to the right. I'm going to draw a loop tilted at an angle relative to that field. The convention that's used to define a single vector from which we orient the field is to choose a vector that is normal to the area itself. What does the word normal here mean? Perpendicular. This is a hard thing to draw, but if I get the visual for the loop again, my normal vector is this red marker. So it's coming out of the screen here, and as I rotate the loop, the normal vector is always perpendicular to the plane defined by that loop. And that's why we use a normal vector, is that a loop defines a plane, and so the only way to get a straight line direction is to look at a line perpendicular to the plane defined by the loop. So it's a useful convention to use, and so that is the one we will use. The angle theta that we often reference then is the angle between the magnetic field and the normal vector. So this angle there is theta. So theta is, by convention, the angle between the magnetic field and vector normal to the loop's area. Don't talk to your neighbor. Don't talk to your neighbor. We are trying to look at a component of the area which swallows up the field, that allows the field through it. Will sine or cosine will function in that case. Don't talk to your neighbor. If we want to look at how much flows through the loop. The question is, in order to maximize the amount of field, is it helpful if the normal vector is in the direction of B or perpendicular to B? How do we get most of the field to flow through the loop? 3D model again. 3D model again before we answer. Here's the loop. Here's a normal vector to that loop. Here is a field that we want. Actually, let's come toward you. There's a field through that loop. If we want that to happen, should the normal vector be perpendicular to the field? If we want the loop to flow through, will it flow through that way? Do we want the normal vector to be parallel to? If we want it to flow through. So how do we get a component of the normal vector field sine or cosine? How do we get the normal vectors component, perpendicular component? Cool. Cosine is the winner here. So our Flux definition then is B area that's perpendicular to the field, which if we use the conventional angle times A times the cosine of angle. It is so easy to forget the normal and that table. So it's important to remember this definition or this convention. Don't forget this convention. It's easy to forget. Questions on what flux is before we talk? All right. Let's back up.